So that was some good reminder of what transpired in the previous lesson. If you want more details, you can go and watch the previous video. So now, with compounds of halogens, mainly we shall talk about halides or hydrides. Okay, we shall mainly talk about hydrides. And what are hydrides? Those are a halogen, okay, that is combined directly to a hydrogen, or you can say HX, where X can be chlorine, it can even be fluorine, X can be chlorine, X can be bromide, and X can be iodide. So these are the hydrides sorry, that we shall talk about in today's lesson. Now for these hydrides, man, let's first have a look at this table. Let's first have a look at the table. Let me take this one because here it is the one which reminds me that you am off. Now, so for the hydrides, oh, sorry for that. If we check the bond energy, the bond dissociation energy, we see that the bond energy decreases down the group. Okay? Can you notice that? We are seeing 5, 5, 6, 4, 3, 1, 4, 3, 3, 3, 6, and 2, 2, 8. So, the bond energy decreases down the group. So, based on this data, you can tell the strength of the bond. You can tell the strength of the bond. You can tell, based on that energy, the bond length. Okay? You can tell the bond length and how is the bond length going to vary down the group. Okay? And having all this, then you should be in position to briefly explain. Okay? And I've really explained a lot. And you are the ones who are going to explain these variations. Now, for boiling point, we can see that for hydrogen fluoride, it is abnormally high. Okay? Then, from hydrogen chloride, normally, there is an increase in the boiling point. Are you able to see the increase? From negative 85 to negative 66, that's an increase. Then, to negative 35, that is also another increase. Okay? There is an increase in the bond dissociation energy. Sorry, in the boiling point. So somebody also should be able to explain that. Then for the Ka, or the acid dissociation constant, we are seeing that there is the acidity is increasing down the group. Okay? The acidity is increasing down the group. You see with this one, okay? The Ka is just 5.6 times 10 power negative 4. This is, I think this one's supposed to be power negative 7. Yeah. Then this one also power negative 9. And this one power negative 11. So the acidity increases down the group. So now, can I receive suggestions? Can I receive who should go for bond dissociation energy? Just chap chap, because we have discussed all this. Why is the bond dissociation energy decreasing down the group? Why is the boiling point? Why does this one have an abnormally high, and whereas the rest, the boiling point increases down the group? And why does acidity increases down the group? Who should go for this? Should we also follow that order? Who should go first? Okay, let's follow the order. Otim first, followed by Amanya Jordan, followed by Mawere Mark. The floor is yours.
The bond energy decreases down the group. This is because the atomic radius increases, which reduces what? The nuclear attraction for the bonding electrons. That's increasing the what? The bond. That's increasing the bond length, and hence it becomes weaker.
And
The
hence,
longer the bond that, and hence becoming weaker. The longer the bonds, that means it will become weaker also. But that's why it's decreasing down the group. But fluorine is, however, fluorine is different because it has a relative higher, because it has a very small radius.
it has a very small radius, and so it strongly attracts the electrons,
Yes.
and making the bond to be short and hence strong.
So,
So requiring too much
yes.
energy to be broken, or releasing too much energy when the bond is broken. No, you require energy to break the bond, and you release energy when the bond is formed. Okay? Yeah, that was pretty good. Okay, Amanya Jordan.
Like as we are seeing the chlorine, bromine, and iodine.
No, we are comparing
Fluorine is an exception.
we are comparing hydrogen fluoride. They are hydrides.
Yes, yes.
Yes, go ahead.
The hydride of fluorine.
Mm.
Fluorine is an exception because it has a more positive boiling point, which is relatively higher, greatly higher than the other ones, and you see relatively the boiling point increases down the group. So, like on hydrogen chloride, the hydrogen bond that is formed is more strong,
Okay,
which
somebody's
needs a lot of,
somebody's talking
which
about
needs, which,
the hydrogen bond. Yes, go ahead.
which leads to this high boiling point. And
Okay.
these ones, the HCl, HBr, and Si have weak van der Waals forces of
Okay.
attraction. As they
Somebody's
move down the group,
somebody's talking about Van der Waals forces of. Okay, go ahead.
as we move down the group,
Yes.
these van der Waals forces become more weaker.
Okay.
As they become more weaker, the more heat, more boiling point is obtained by these elements as we move down the group.
And some correction. As you go down the group, the strength of Van der Waals forces of attraction increases.
Yes,
Uh-huh.
van der Waals forces become more strong as we move down the group. Hence, more heat is required by this hydride of iodine as compared to as compared to HCl.
Hmm.
Hence, their boiling point increase down the group.
Okay, that's really good. That's good. That is good. So this the magnitude or the strength of the van der Waals forces of attraction increases with increase in molecular mass, with increase in the size. You remember when we talked about the bonding? There is a video you can also go and watch it. We saw that as the size of these atoms increase, the atoms become more close together. And so when they become close together, they strongly attract each other, which increases the magnitude of the van der Waals forces of attraction. So as you go down the group, the molecular mass increases, the atoms become more, their sizes increase, and so the strength of the van der Waals increase, and so more energy is required. However, as you've said, for fluorine, for hydrogen fluoride, for it, it's abnormally high. Hmm? Abnormally high. Why? It's because the molecules of hydrogen fluoride do exhibit the hydrogen bonding. And these hydrogen bonds are far, far stronger than the van der Waals forces of attraction. Hence, more energy required to break them. Anyway, we are going to talk about each. Yes, Mawere Mark. Mark? Okay, yes, Mark, we can hear you.
The hydrogen fluoride of 5.6% or -4.
Your voice is a bit down. Can you try to
Hydrogen
amplify? Can you try to amplify in the voice?
let's say that of distillation constant according to me. Uh, hydrogen fluoride, hydrogen iodide, like pictures here. Hydrogen fluoride and hydrogen iodide.
Ah, I think Mark, I don't know what is wrong. Mark?
I was like, according to me,
Yes.
for for acidification constant,
Mm.
right? Uh, the acidification constant of fluoride
Mm.
5 which is bigger than the rate of reduction of the group, right?
Ah, you are on and off. Sorry to say that, but you are on and off.
The that is which is bigger than the rate, which means that
Mm.
as you go down the dissociation constant of the acid
Mm.
reduces. So I think the hydrogen fluoride dissociates more compared to the rest of it,
Oh,
right?
okay. Okay, go ahead. Yes, Mark.
You're finished.
You finished, eh? Okay, you can try to tell us. You can try to explain. Okay, the issue is the acidity decreases down the group. Sorry, the acidity increases down the group. Sorry for that. So why the acidity? Why does it increase down the group? Okay, that was good. Somebody who wants to give it a shot? Who wants to add on what Mark has told us? No one?
Let me try.
It's okay, Jordan.
Like you said that it's a dissociation constant of these hydrides increases down the group.
Yes?
The HCl, the HBr, and the Fi down the group as it increases. These ones dissociate more to produce hydrogen ions than than HF, which has the least constant,
Mm,
which makes this constant increase down the group.
mm. Okay, okay. Okay, that's fair. That's fair try. I think these values they are the ones which are bringing troubles here. These values they are bringing troubles. Now they are not sorry, they are not negative. Let's remain the way they are. Now the way these values are gotten is if this is your acid, okay, okay, and the acid dissociates in aqueous, it will give you hydrogen ions. We shall study this in ionic equilibrium. Aqueous, okay, and then plus the X, the hydrogen ion, okay, minus. Now the Ka is going to be the values they are positive. Let them stay the way they are. Now the Ka is going to be the concentration of hydrogen ions, okay, the ionic product in other words times the concentration of halogen ions out of the concentration of the acid HX. So now what does this mean? If the ionic product, okay, if the concentration of these products is less than the concentration of the acid, then the value is going to be very small. But if the ionic product, okay, of these ions is far higher than the concentration of the undissociated acid, then the value is going to be big. So from what we can see, unfortunately I can't take away this, but in a recorded video it won't be there. So we can all see that the Ka increases, okay, down the group. Now why is it increasing? It is because of this, okay. The explanation here is the one that is explaining this, okay. Anyway, we are going to see, it's what we are going to talk about, but this table has helped us to clear everything. Now the acidity is increasing down the group. Why? The acidity depends on how easily this bond is broken. The hydrogen halide bond, how easily the bond is broken. So if the bond is easily broken, then you will easily dissociate to release hydrogen ions, hence accounting for the high acidity. But if the bond cannot easily be broken, the bond is strong, too strong to be broken, okay, then you don't easily dissociate to give hydrogen ion, hence the decrease in acidity. So if you have to check on the bond energy, let's check about this. Check on the bond energy. You can see that the strength of the bond is decreasing. The bond becomes weaker and weaker as you go down the group. Can you see that? Yes. And so as a result, such a weak bond is easily broken in an aqueous solution, okay, which will account for the decrease, sorry, the increase in the acidity, okay, in the acidity of our hydrogen acids or halogen acids, okay. Yes, that was some good submission from you guys, and I'm really amazed. So let's talk about these few chap. Boiling point increases from hydrogen chloride, and you are able to say this, to hydrogen iodide. Why? They are simple molecules with simple covalent structures, okay, and so those covalent structures are held together by intermolecular van der Waals forces of attraction, whose magnitude increases with molecular mass. We talked about that, and we are seeing that from hydrogen chloride to hydrogen iodide, the molecular mass increases, and so the increase in boiling point. However, for chlorine, for hydrogen fluoride, in fact, if you are to plot on a graph, you see that you have such, where this one will be the boiling point of hydrogen fluoride, and then boiling point of hydrogen chloride, and then some increase, okay. So this is hydrogen fluoride, hydrogen chloride, hydrogen iodide, and hydrogen iodide, and this is hydrogen bromide, and then this is hydrogen chloride, and this is hydrogen fluoride. So you're getting such a graph. So with hydrogen fluoride, for instance, okay, it has an abnormally high boiling point, and the answer goes to hydrogen bonding. So I'll still take you back to bonding, where I told you that with hydrogen bonds, where hydrogen is directly bonded to fluorine, or where hydrogen is directly bonded to oxygen, and hydrogen is directly bonded to, why these two? Because they are the ones which are very electronegative atoms. They are highly electronegative atoms, and so because of that, they end up polarizing this hydrogen fluoride bond, hydrogen oxygen bond, and hydrogen nitrogen bond. So as a result, you end up forming a hydrogen bond among the molecules of hydrogen fluoride, and these hydrogen bonds are too strong to be broken by just, which accounts for a high boiling point of hydrogen fluoride. Is that good? Yes, so molecules associate by hydrogen bonding due to small ionic radius of fluorine. With bond energy, it decreases from hydrogen fluoride due to the decrease in atomic radius. Due to the increase in atomic radius. So as you go from hydrogen fluoride to hydrogen iodide, the atomic radius increases, which increases the bond length, and so easily broken. So also decrease in electronegativity down the group, the bonds become less polar, okay, and so if they become less polar, then they become Okay, the bonding electrons are not strongly attracted. And if the bonding electrons are not strongly attracted, then it becomes weak and easily overcome. Acidic strength depends on how easily an acid dissociates, and so the concentration of hydrogen in an aqueous solution. Is that okay? And since the electronegativity decreases down the group, obviously, due to the increase in atomic radius, and the bond strength of these halogen acids decreases, the bond strength decreases in this order, where this one is most strong or the strongest, followed by this, followed by this, followed by this. Okay? And so the increase in acidity. Because the bond is easily broken, a weak bond is easily broken. A strong bond requires too much energy to break the bond. And so if it doesn't easily break, then it doesn't easily release hydrogen ions, hence becomes the weak acid. But for hydrogen iodide, with the weakest bond in aqueous solution, it easily breaks and easily releases the protons. So basically, it is as simple as that. So, any questions as far as what we've talked about is concerned? So, like I told you, inorganic chemistry is all about the periodic properties and some few reactions. So, I hope you can see to be able to explain how this is going to vary.
Excuse me, sir.
Yes, Innocent.
Excuse me, sir.
Yes, Innocent.
I think I need a pardon on the explanation of it. I need a pardon on the explanation of acidic strength.
Okay, acidic strength. It's okay. That's why you're here. It's okay. So we say that maybe the acidic strength depends on how easily you can release the protons in an aqueous solution. The higher the electrons, the higher the protons, the lower the pH, the higher the strength of an acid. Okay? And you easily release protons if you can easily break the bond between the hydrogen and something that is bonded to it. For example, let's take this. Okay? You have HX, and we are good enough, we are studying halogens, where X can be fluorine, X can be chlorine, X can be bromine, and X can be iodine. Now, for you to become an acid, you must be able to dissociate and release only hydrogen ions as positively charged ions, okay, to form hydrogen ions. I won't write states, sorry for that. And then, okay, and halogen ion. Now, depending on how easily you can lose this proton, depending on the amount of hydrogen ions in this solution, it determines how strong the acid is going to be. Does it make sense? The ease of releasing hydrogen ions determines how strong the acid is going to be. So down the group, as we can see, for hydrogen fluoride, the bond is too strong. The bond is too strong. Why is it too strong? Because the fluoride, this fluoride atom is too small, the hydrogen is too small. So these bonding electrons are strongly attracted. That the covalent bond that is formed is strong, too strong to be broken. But for hydrogen iodide, for instance, this is a large sized atom. It can be like this. Whereas the hydrogen can be like this. Can you imagine? So this large atom, it strongly forms weak covalent bond. Okay? These electrons are not strongly attracted to the nucleus. Okay? So that the bond length of this hydrogen iodide bond is too long. The bond length is high. So that when you come to break this bond, you break it with ease. Baganda say, as osindisa stamie. Banyankore say, what do you say? Wasind korotami. Now, I don't know how my Arul friends say. If we have one here, you can help us. But it's like pushing somebody who is quoting to see. That is a direct translation. So breaking this bond, it easily breaks with ease. Okay? So that the rate at which you release hydrogen ions in aqueous solution is so high. Okay? So high. Oh, sorry. Plus iodide. So high. Okay? That when you measure the concentration, remember pH. Okay? pH, it is the measure of negative log of concentration of hydrogen ions. So if you measure the pH for this solution, since the hydrogen ions is the concentration of hydrogen ions is so high, the pH is going to be less, like 2. But for this one where you have very few concentration of hydrogen ions, you have a pH which is almost like 6 or 5. You can imagine. So this one therefore becomes more acidic than this solution. Have I explained? Yes. So now let's see how these halogen acids react. And they are acids, and this is the easiest, I think. You studied senior 2, you remember how acids. So they are the same things here. So in aqueous solutions, they are acids. They behave as acids. Okay? In aqueous solutions. Whereby, apart from this, the rest are strong acids. Whereby if you react it with any metal, okay, it will liberate. So I've never seen a gaseous metal. So if you react it with any metal, it will liberate hydrogen gas, okay, with NH, okay, and this is aqueous because you are reacting it in an aqueous solution. Then it will liberate hydrogen gas, okay, and then a metal salt is formed, MgX. A metal salt is formed, and this one is an aqueous solution. So it is basically as simple as that. It's as simple as that. So they are high. Now this one happens. Hey, did I say? Okay, magnesium for instance, okay? So I didn't intend it. I didn't intend to use magnesium. I just wanted to use M. Where this M represents metals that are highly electropositive. Metals that are above hydrogen in the reactivity series, in the electrochemical series. Otherwise, if it is lower than hydrogen, for example, copper, now copper, it won't be able to displace this hydrogen from its halogen acid. Is that okay? That's brilliant. For hydrogen fluoride and hydrogen chloride, they won't be able to react with conc acid. Okay? But the rest, they do react with conc acid to liberate sulfur dioxide gas. The rest for hydrogen bromide. Somebody's calling me. A moment. So I can call them. Oh. For the rest, for hydrogen bromide and hydrogen iodide, they are strong reducing agent. Therefore, they are able to oxidize sulfuric acid to bromine and iodine. Okay? So you can, if you have your conc sulfuric acid, okay, and you react it with this is, okay, let's say liquid. Why liquid? Because it is conc sulfuric acid, and you react it with hydrogen iodide. Okay, hydrogen iodide. This is maybe aqueous. The hydrogen iodide is going to be oxidized to iodine. Okay, why oxidation? Because, okay, this is aqueous. Now why oxidation? Because this one is in -1 oxidation state and this one is 0 oxidation state. And then the conc acid, for it will be reduced to sulfur dioxide gas. Okay, sulfur dioxide gas and the water. So try to balance this equation, and this is liquid. So if you try to balance, if we put a 2 here, no, the 2 won't be enough. So these ones, they are 6. Okay, so we have 2, this is 4, but we need 2 here. I hope that one is balanced. So oxygen, yeah, it is balanced. So that is your equation. Okay, so we have, let me put the figures. So we have a 2 here and a 2 here. The rest is balanced. Yeah. So I hope the equation is okay. I hope the equation is okay. So we have a however with the conc HCl, it can also be oxidized by strong oxidizing agents such as manganese 2, and then lead 2, and then potassium permanganate. Sorry, this is lead 4. And to write these equations, you can easily write them using half equations. Like for manganese, you can use a half equation, and for potassium permanganate, you can also use a half equation. And now for me, I'm going to write this, you write the rest. So for PbO, okay, for PbO oxide, okay, this is a solid. You can write it reacts with conc HCl, okay, conc HCl. Maybe we can put aqueous here because it can't be 100% HCl. So it is oxidized to lead 2. Can it be lead 2 chloride? Aqueous, and then plus chlorine gas, and then plus water. So you try to balance that and see if it may come out. So we have to this side. So if you put a 2 here, and a 2 here, yes, our equation is balanced. Not a 2, a 4. It's a 4 here, so we shall put 4 and a 2 here. So now our equation is balanced. So this one, our red 2 oxide, it is oxidizing the hydrogen, the hydrochloric acid, to chlorine. Okay, and for it, since here it is in +4 oxidation state, it is reduced to +2 oxidation state. So that's what we call a redox reaction. Similarly, you can do the same for this. Okay, we can do the same for this, for potassium permanganate. Why don't you try it out? But anyway, here you use half equations and high chances that you haven't studied half equations. So with potassium permanganate, okay, so now for this one, for potassium permanganate, here we can use half equations. Okay, and you write MO 4 minus, and this is aqueous, then it gets acidified. Okay, acidified. Okay, aqueous, then we shall get, it will be reduced to manganese 2. Okay, 2 plus, and then plus the water, and this is liquid. Then we can put a 4 here. Why 4? I want to balance the oxygens, and if we put a 4, then we shall need to put an 8 here. Why 8? Because this is 4 times 2. Now we need to balance the charge. The equation is balanced, but the charge is not balanced. So you can see we have 2 positives here. Okay, and we have 1 minus here and 8 pluses. So how should we balance? Okay, so this one, 1 minus 1 minus, it becomes plus 7. Okay, so how should we reduce this plus 7 until it balances to +2? We shall just add 5 negatives. Okay, so if we add 5 negatives here, then we shall balance, okay, the charges. So, and you know that electrons are negatively charged, so we shall put our 5 here. That's one. Then for chlorine, okay, it is just chloride aqueous to give us the chlorine aqueous. Okay, let it be a gas. So if we balance, we shall put a 2 here. Now the charges, we have -1 here, but this side we have 0. But -1 times 2, that's 2 minus. So if we put the 2 minus this side, our equation shall be balanced. So after writing this, then simply we shall multiply, cross multiplication, so that we cancel these electrons. So if we put a 2 here and we put this 5 here, somebody should ask, where is the 2 coming from? We want to eliminate these electrons. Okay, so we are using elimination method. So if we put 2, it will be 2 times 5, which is 10, and then 5 here, it will be 2 times 5, which is 10. So we cancel the electrons. So if you cancel, then you shall write everything the way it is. Maybe let me write it here. So it will be 2 times manganese, so it will be 2 MnO4 minus aqueous, then plus 2 times 8, that is 16, hydrogen ions, okay, aqueous, plus 5 times 2, which is 10 Cl minus aqueous. What shall we get? We shall get 2 times this one, so it is 2 m n 2 minus 2 plus aqueous, okay, plus 2 times the 4, which is 8 water, and that's a liquid. Finally 5 times 1, so plus 5 Cl. So if you do this, your equation is going to be balanced. So I hope it is okay now. For manganese oxide, same thing. I'll just write the half equation. Manganese oxide, and this is a solid. It is dissolved in an acid, okay, and this is aqueous to form manganese ions, and then this is aqueous plus water, and this one is a liquid. So if you try to balance, there is a 2. If you put a 2 here, and we put a 4 here, the charges, are they balanced? We shall put 2 electrons. So this is the half equation, and then you write another half equation for chloride ions, okay, and then to give you chlorine, and then the 2 electrons with the 2 here. So if you cancel the 2, then that becomes the equation of reaction. So I hope that one is okay to everyone. Now, however, for hydrogen fluoride, still it is a special case, okay? It reacts with silicon fluoride to form hexafluorosilicic acid. Hexafluorosilicic acid. So you have HF, okay, and this is aqueous. So our HF reacts with the silicon chloride oxide, which is SO4. Oh, this is a 2. Now I can't wrap, everything goes. So this is a 2. So this one becomes HF, aqueous, reacts with silicon oxide, this is I, okay, and this is a solid. We shall form hexafluoro, so that means those are 6 F, hexafluorosilicic. So silicic, something of this kind, hexafluorosilicic acid. If you try to balance, is this 2? You can try to find out, is that 2? Anybody who has finished? Okay, so this O is not there, the O is not there. Okay, it is just F6 and then S, the whole of it is a complex with the 2 minus. So if I'm to write, it is going to be HS, H, okay, H2, same thing, and then I write my S, and then I put F6. Yeah, something of this kind. So the whole of it is a complex. Okay? Yes, and then I think the O combines with hydrogen to form the water. So you can fact check this equation, okay? Yes, you can check our notes, this equation is there. What is wrong? So you can still see the unique properties, you can see the unique reactions, how fluorine is unique. The rest, there is no other acid that can react with. Actually, the equation is here. Yeah, the equation is here. So hydrogen fluoride or hydrofluoric acid reacts with silicon to form hydrofluoric silicic acid or silicic acid plus the water. So questions, can you try to answer this in the chat box? Explain the following observations. When hydroiodic acid is exposed to air, it turns brown. Then a colorless solution of acidified hydrogen peroxide turns brown on addition to potassium iodide. So these are some good questions, but you answer this one A, then you answer this in your free time, and even write the equation of reaction. So anyway, like I said, I'm going to answer this and you will answer this. So with hydroiodic acid, when it is exposed to air, it will react with oxygen. It will be oxidized, okay, with oxygen to form water, okay, and then the iodine aqueous. Now it is this iodine, you know that the color of iodine is brown, okay. It is this iodine that will turn the whole solution, okay, to be brown. This iodine that is formed. Now if you have to balance, maybe if we put a 2 here, okay, now the oxygen has issues, maybe we put a 2 here and a 4 here and a 2 here, okay. Our equation is now balanced. Now you react, you answer this, even you write those half equations and you write formula overall equation, and maybe I'll post that question in our classroom. Yeah, I'll post the question in the classroom. With oxo acids, now all halogens, they do form oxo acids. Now what are oxo acids? They are here. The HOCl, HOCl2, HO, HCl3 and HCl4. This is perchloric acid, or perchloric acid. Then this is a chlorate. This is perchlorate. This is a chlorate. And this is chlorus, and this is a chloride. So these are the oxo acids. And if you are to study their structures, okay, I think that's what should come next. Yes. So if you are to study their structures, you see that if this is chlorine, or in all, the chlorine is the central metal atom. Okay? In both hypochlorite, in both chloride, hypochlorous, chlorate, and perchlorate. Now in both, chlorine is a central metal atom. And in this, the chloride is in +1, okay, oxidation state. In this, the chloride is in +3, oxidation state. And in this, the chloride is in +5, oxidation state. And in this, the chloride is in +7, oxidation state. Now, why are they able to form these oxo acids with oxygen? It is because for oxygen, if you compare oxygen with other halogens apart from fluorine, the oxygen is highly electronegative compared to these halogens. It means that when these high halogens react with the oxygen is going to induce these high halogens to form positively charged ions. But for fluorine that is highly electronegative, it resists that. So it won't be able to form the oxo acids. So for example, if you are to write this, the chloride Cl minus, this is what I'm going to draw. The chlorine becomes the central metal atom and it is bonded to one oxygen. So out of 7, you have used how many? 1 electron to covalently bond with the oxygen, and so as a result, you have 6 electrons that are not bonded. So they arrange in pairs to form the 3 lone pairs of electrons. Okay? To form 3 lone pairs of electrons. So they are these lone pairs of electrons that will arrange themselves, okay? That will arrange themselves within the structure of the chloride, okay? To form the chloride with an minus on oxygen. So if it is the acid, then you just put the OH here. Then for chloride 3, you can see it is HCO2. Okay? So you have used it now with a minus. Now one oxygen has used 3, so it has used 2, and the other one has used 1. So you've used the maximum of how many? 3 electrons. So the chlorine will remain with 4 out of. Remember, it has 7 in the outermost shell. So 7, it has used 3, so it has 4. And so how many lone pairs of electrons? Those are 2 lone pairs. So you draw your Cl. So you put 1 lone pair here, and you put another lone pair here somewhere. We shall study all this in physical chemistry. Actually, on assumption you studied them. These are one of the very first topics in physical chemistry. So it will have such a structure, the V shape. Then for this one, you can see it has used 5 electrons to covalently bond with oxygen. Okay, you see it is ClO3. So the oxygen, there are 3, and each oxygen can take a maximum of 2. Okay, but it has 1 charge, so minus the 1. So you can see that it has used 5. And how many lone pairs of electrons does it have? It has 7 outermost electrons minus 5 electrons used in the bonding, so it has 1 lone pair. Okay, so therefore it will have such a shape. You have your lone pair here, and you have 1 oxygen somewhere here. You have another oxygen going the other side. Okay, and then you have another oxygen here. So, and Cl7, now this one is in +7 oxidation state. So if you are observant, you can observe that the oxidation states of these oxo acids, they are odds. You see +1, +3, +5, and +7. You can't find any even number. You can't find a chlorus 2, no. You can't find a chlorus 4, no. Why? Because chlorine forms oxidation states in odd numbers. Okay? That's why to form +1, +3, +7, and +5. +5 and +7. I hope it is okay. Any queries? So we can proceed, since there are no queries, we can proceed and look at the acidic strength, okay, of these oxo acids. Now the acidic strength depends on how many oxygen atoms do you have. How many oxygen atoms do you have? For example, let's have a look at this. Oh, I need a red, not this. So let's say you have this, okay, the Cl, and the Cl has just one oxygen atom. It is not. So it is just the Cl, okay, with one OH. Then you have another Cl. Here you have one oxygen, okay, and then the OH. Then here you have the C with 3 oxygens. You have one there, you have another one here, okay, and then you have OH, okay, and then finally you have the C. You have the C, you have oxygen here, you have oxygen here, you have oxygen here, and you have the OH. Now from our initial topics, still periodic properties, that topic, I will always talk about it. I will always comment about it, that topic. So from this, we all know that oxygen is highly electronegative, okay, than the halogens, okay, that it is going to attract the bonding electrons from the halogen towards itself, increasing the electron density on the chlorine, okay. And so what does that imply? The more the electron, the oxygen atoms around this central metal atom, the higher the electronegativity around this central metal atom. For example, have a look at this. This one will attract the electrons. This one will attract the electrons. And this one too will attract the electrons. Okay? Now what will be the result on this chloride atom, that is the central metal atom? It will become highly electrophilic. Okay? Highly electrophilic. Okay? That as a result, if this chloride becomes highly electrophilic, to try to balance the equation, like how you say this these days, to try to balance the equation, it will try to withdraw the bonding electrons from the Cl oxygen bond here, okay, and the same effect is going to be distributed to this oxygen hydrogen bond, okay, which will weaken this bond. It will weaken this bond, hence easily released, okay, to aqueous solution. And if you easily release this proton, then your acidic strength increases. But for this one with very few, actually this one, why should it release this hydrogen ion? It is released because the oxygen is highly electronegative, so it will attract the bonding electrons from the oxygen-hydrogen bond. But if you add there the oxygen, so this one attracts, then this one will distribute the same effect on this bond, hence on the oxygen-hydrogen bond. Hence you easily release the bond. Again, you increase the number of oxygen atoms, the same thing, same case. You increase, this one attracts, and also this one attracts. Then you distribute the charge, the effect, on the oxygen-hydrogen bond, okay? And as a result, the same effect is distributed on the hydrogen-oxygen bond, which is easily released into the solution. You increase from 2 to 3, now the effect becomes pronounced. So as a result, the more the oxygen atoms present on the oxo acid determines how strong the bond, the acidity the oxo acid is going to be. So oxygen is more electronegative than the chlorine or the bromine or the iodine, depending. So it pulls the bonding electrons towards itself, and this negative effect is transmitted to the oxygen-hydrogen bond, hence weakening it, easily releasing the proton in the aqueous solution. As simple as that. Now, should you really fail to explain this simple concept? Should you really fail? Okay? Yes, so let me wait for questions from you guys and see how we can attempt them. So, since there are no queries, it's okay. Seems everything is okay. Now, the greater the number of hydrogen atoms, the greater the effect, and the weaker the OH bond. Hence the ease of releasing the OH bond to the solution. And the acidic strength therefore is going to be in that order. Okay? Yes, so this is the order of decreasing acidity. Now there is some question, there is some logic that tend to. They say, explain the order of decreasing acidity among the oxo acids. And somebody, the question wants the order of decreasing acidity. And somebody writes this. HF, HCl O4. Okay? We want order of decreasing, and somebody writes this. No, this is okay. Some people can use this sign. HCl3, and somebody writes this. The SO2 first says the order of decreasing acidity is in, and then somebody writes this. Now from your primary science, this one means less than. So if you write this, it means that this is less acidic than this, and it's not the case. One can write this. The question wants the order of decreasing acidity, and somebody writes this. The order is like this. SCl2, SCl3, and then HCl4. Somebody writes this. Yes, the order is okay, but you are not answering the question. This is order of increasing acidity, but the question wants the order of decreasing acidity. So still we shall cross you. You are not answering the question. You are answering your own question. Is that okay? Yes. I hope it is ready. Okay. So how they are prepared? Simple. The chloric acids are obtained when chlorine is bubbled just through water. Okay? You remember the reactions, the equation. So chlorine, you remember these equations. The chlorine, okay, reacts with water. This is a gas, okay, with water, and the water is a liquid. Then we shall form what? Hypochlorous acid. You can write HOCl and then sodium HCl. Okay, this is aqueous. So we have prepared the chloride. Okay, the chloride or the chloric acid. Then for chlorates, for example, the chlorus, the ClO2. These ones are prepared by bubbling chlorine in dilute alkaline solutions. I hope you still remember this. Okay, chlorine bubbled in aqueous. This is OH. This is chlorate 1. This is OH. And then this is aqueous. This is gas. Then we shall form sodium hypochlorite. Okay, that is if it's a sodium. We are interested in sodium plus the water. So, but now for chlorate 5, okay, so the equation is there, plus chloride, and these ones, they do decompose to give oxygen and the chloride. This one, should I write the equation? No, we wrote the equation. Then for chlorates, they can be prepared by so in presence of an acid, the chloride ions can act as oxidizing agents, i.e. where they can oxidize iodine to iodate ions. Now there are a lot of equations that we are going to write. So you have the chlorate, okay, and this is aqueous. When it is acidified, okay, hydrogen ions, then we shall form a chloride, okay, and water. So try to balance. So we shall need a 2 here. I think the equation is balanced. Now remaining with the charges, so we shall put a 2 here, because this side we have -1, and then +2, so we shall just put to balance the charges. Now for iodine, same thing. It oxidized iodide ions, okay, aqueous to iodine, iodine, and this is aqueous too. And so if we balance, we shall put a 2 here and then +2 electrons. So just cancel this and write everything. So that will be the equation. Now this technique of using half equations, it's really good. Really good. You should know half equations for all where possible. Okay? Yes. So in aqueous solutions, they do undergo what we call disproportionation reaction. Now with this, the disproportionation reaction, this is a reaction where a compound undergoes what we call self-oxidation and reduction at the same time. Same equation, but the compound is undergoing self-oxidation and reduction. For example, this is your chloride. Okay? This is your chloride 1. So in aqueous solution, it will undergo self-oxidation where it will form a chlorate. Okay? Cl. This is Cl3 minus aqueous, and then the chloride ions. So this is what we call a disproportionation reaction. So if we try to balance, if we put, this is aqueous, if we put a 2 here and we put a 3 here, our equation will be balanced. So it's as simple as that. Then, and that one occurs in aqueous solution. Now with concentrated HCl, the chloride ions, they are reduced now because this is oxidation. They are reduced to chlorine gas. Okay, and the acid itself is oxidized to chlorine gas, and you produce your chlorine gas. Then the reaction above is used to determine the percentage of chlorine in a bleaching agent. So you can copy this question, you go and do it. And we call it a day. So you just take a screenshot of this question. Take a screenshot of this question, maybe to interpret it for you. So we have 0.6 centimeters cubed of sodium hypochlorite, and the GIC is sodium hypochlorite. So that's how we write GIC. Is dissolved in water and the solution made up to 250. Then 25 of that solution is acidified by 10 of 0.8 is acidified. You use, now in this case we shall use sulfuric acid to acidify, and then 10 centimeters cubed of potassium iodide is also added. So after acidifying, you add 10 centimeters cubed of 0.2 molar potassium iodide. So all these are key. Now what does this mean? The hypochlorite, depending on the other equation I wrote for you, okay, you can go back and check. Yes, the equation I wrote for you, it is going to oxidize the potassium iodide, okay, to iodine. Now this one must be in excess, the potassium iodide must be in excess, so that all of this reacts. Okay, so that's why you're using 10 centimeters cubed of 2 molar, 0.2 molar potassium iodide, and it's enough. Then the liberated iodine is going to be titrated with sodium thiosulfate. Maybe I can give you the half equation. It is S2O3, then 2 minus aqueous, oxidized. Is it oxidation or reduction? You can calculate the oxidation states. This is SO4, then O3, no, O6, then 2 minus. Now if you are to balance, we shall put a 2 here. Yeah, this is oxidation. And then 2 here. So this is the half equation for sodium thiosulfate. So the sodium thiosulfate is going to react with iodine that is liberated. Okay? Now, this is what you put in a burette. Okay? And you titrate. And when you titrate it, you obviously use a starch indicator to show you that the reaction is complete. So when you titrate, you find out that you need 5.0 centimeters cubed over 0.2 molar sodium thiosulfate for the reaction to become complete. And the question wants the percentage of chlorine in the jig. So this is homework. Please go and do. I'll be amazed to receive your answers before our next lesson.